Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore momentum. So what is momentum? Well, momentum is basically a component which is made up of two main variables. Those variables basically are mass and velocity. And they're really useful, or momentum is really useful to measure things like collisions and explosions. And we use the concept of momentum along with the idea of center of mass, which we explored earlier, to determine what happens or has happened to an object that has either collided either on a one-dimension, two-dimensional, three-dimensional plane. So momentum basically, as I stated, is made up of mass in kilograms, velocity in meters per second, and momentum has the units kilogram meters per second. So it's a vector quantity because velocity also happens to be a vector quantity. So as a result, all the information, the concepts that we've learned about velocity as a vector will apply to the same scenario as in momentum. This is because the mass is a constant. In the units that we're going to be studying, we're not going to be losing any mass. So as mass remains constant before and after a situation, the only thing that's going to change is the velocity. So things like change in velocity are going to apply in the same way in momentum as they did in our velocity units. Now basically what we tend to find is that if we've got an unbalanced force which is applied on an object, Newton's laws basically state that we're going to change the velocity. So by acting a force, we're going to accelerate or change that velocity. So as a result, we change or accelerate the momentum. And as a result, this can be calculated from the algorithm that change in momentum equals the final momentum minus the initial momentum. As this can be utilized as a vector, we can use the idea of the negative initial momentum as being a change in direction of that initial momentum, if that makes sense. So obviously if my initial momentum was going east, if I was to incorporate it into a vector triangle, then it would have to be going west to find the change in momentum. This is going to be what causes that change in velocity in that first place. Okay, so let's start off and just have a look at an example of how we utilize the algorithm, and then we'll go on and have a little bit more of an involved example looking at change in momentum. So here we've got an example where we're going to calculate just solely the momentum of a 2 kilogram bowling ball which is traveling at 8 meters per second south. Note that the velocity has been mentioned in the form of a vector, so the momentum must be stated as a vector with a magnitude and a direction. So pause it for a moment, see if you can calculate the momentum of this bowling ball. Okay, welcome back. So how did you get on? Well, let's have a look. So the solution here, we're going to be using momentum equals the mass times the velocity. The mass is 2 kilograms. The velocity is 8 meters per second south. So the momentum overall is 16 kilogram meters per second south. How'd you get on? Pretty straightforward, eh? So now you can calculate the momentum. The next example I've got for you is where we're going to be looking at the change in momentum. So remember that the change in momentum basically is the final momentum minus the initial momentum. Have a go at this question where we've got the proton of mass 1.67 times 10 to the negative 27 kilograms is accelerated from 3 times 10 to the 4 meters per second north to 3 times 10 to the 5 meters per second north. So we're going to calculate that change in momentum. So you have to utilize the type of momentum equation as you did in the previous example and then apply it to our change in momentum algorithm. So pause the video now, see how you get on. Okay, welcome back. So how did you get on? I'm sure you did fine. So let's run through how we calculate this. Well, we know that the change in momentum is the final momentum minus the initial momentum. And there's our algorithm. Delta phi equals phi final minus phi initial. Remember that little p is the Greek symbol phi. So as a result, delta phi will equal mv minus mu, or the final momentum mv or mvf subscript, some people might see it, minus mvi which is the initial momentum, or U as we use here at St. Hilda's. Okay, so let's substitute in and find, let's break it up and let's find the final momentum first, followed by the initial momentum. So the final momentum, mv, is going to be 1.67 times 10 to the negative 27, and it's going to be multiplied by the velocity, which is 3 times 10 to the 5. This gives me 5 times 10 to the negative 22 kilogram meters per second north. So that's the final momentum. Let's find the initial momentum. Well, it's the same algorithm. It's the same process. We know it's going in the northerly direction, but what's happened is it's actually gone from, it's 1.67 times 10 to the negative 27 times 3 times 10 to the 4. So it's obviously slower than the final momentum. So we end up with 5 times 10 to the negative 23 kilograms meters per second, but it's in the same direction. Now, to use the algorithm, what I've got to do is to actually change the direction of the initial momentum. So instead of being north, it's going to be south. Now, if I say that north is going to be positive, the change in momentum will be one plus the other, but because it's going in the opposite direction, I need to take it away. So the result of the final, or the change in momentum, is the initial momentum, 5 times 10 to the negative 22, take away 5 times 10 to the negative 23, which gives me 4.5 times 10 to the negative 22 kilogram meters per second north. This is what promotes the change in momentum and allows it to accelerate up to 3 times 10 to the 8 meters per second north. If, for example, it had changed and was going south, then what I would then have to do is then apply my algorithm. And in this case, the negative would mean that we would have to add the values together. So remember that that negative value is all down to the direction that it happens to be going. Stipulate which is going to be positive first, and then rearrange the directions accordingly, and then solve on a single plane. So obviously that's very straightforward when we're dealing with single one plane directions. If we were looking at two-dimensional directions, then what we would then do is we would then use a right angle triangle and use Pythagoras and trigonometry. And instead of it just being velocity, we do it as momentum. So it's exactly the same as we've done before. But we'll cover that, that two-dimensional aspect later on. For now, just concentrate on momentum and change in momentum. I put a worksheet on the post of this course so that you can work through those sorts of algorithms. Well, I hope you found that useful. Thank you for watching, and I look forward to you joining me again. Bye for now.